Complex digital circuitry can often be replaced by what type of integrated circuit? You can use the microcontroller or the microcomputer to replace complex circuitry. Here is, there's that microchip again. Here's some of the stuff that's inside it. There's a CPU. There's a serial port in and out. There's another in and out port, another in and out port here, another in and out port here. There are timers. There's read-only memory. There's a random access memory and read-only memory. So all kinds of stuff going on inside that little chip that can replace a whole bunch of complex circuitry simply by programming it into this, this microcontroller or microcomputer. Which of the following is an advantage of using the binary system when processing digital signals? The reason we do this is because ones and zeros are easy to represent electrically with either an off or an on. Okay, and your signals are just off and on. Now, the number system that we're familiar with doesn't have 2 states like off and on. It has 10 states, 0 through 9. Okay, but that's very difficult to do electrically because then you have to have things in between off and on. So in doing digital signals, we do everything in either voltage off or voltage on. Okay, and that's what we're talking about here in binary. It lets us, the binary ones and zeros, which are the only numbers in binary, are ones and zeros. They're easy to represent with either an off or an on state. Now, this is difficult for people, but it's really easy for machines because they are able to easily distinguish the ones and zeros and deal with them. Now, in a place value chart, if there's a 1 in here, that represents the value 1. In this column, represents the value 1. In our decimal system, we would call this 2. Any 1 in this column represents the value 2. So if I come down here to this one where I have 1, 1, 1 plus 1 is what we would call in the decimal system 3. Or this one, 1 over here in the 4's column, plus 1 would be what we'd call in the decimal system 5. Okay? Or here, 4 plus 2 plus 1 is what we would call in the decimal system 7. Okay? But in the binary system, you have only these 2 different kinds of digits. You have only voltage off and voltage on. All right? So it makes a different place value system than what we're accustomed to in the base 10 system. Which of the following describes the function of a 2-input AND gate? Okay, an AND gate is a logic device. This is the symbolic representation of an AND gate. And it's called an AND gate because the output will only be high if there is a high input on both the A and the B inputs. Okay? So the truth table, if A is 0 and B is 0, the output's 0. If A is 0 and B is 1, the output is 0. If A is 1 and B is 0, the output is 0. And if you have A and B, that's why it's called an AND gate, A and B, then the output will be high or be 1. Okay? So an AND gate, the output is high only when both inputs are high. Now here's a different device. Which of the following describes the function of a 2-input NOR gate? And let's go to the diagram. Okay, this is an OR gate. And this is not what the question's about, but it'll help you understand the NOR gate. In an OR gate, if either or both of the inputs are high, the output will be high. And it's called this or this will give you a high output. Both of them will give you a high output. Okay, that's an OR gate. But what they've asked us about is a NOR gate. And a NOR gate has a little circle out here on its diagram that tells you that the output is inverted, so that the output will be just the opposite of what it would be on the OR gate. Okay, so when either or both inputs are high on the NOR gate, the output is low, as you can see from this truth table here. And if you compare the two truth tables, you will see that the output of the NOR is exactly opposite the output of the OR because of the inverting function that makes it into a NOR. How many states does a 3-bit binary counter have? 3-bit binary counter. Here's the truth table for a 3-bit binary counter. So it has one bit that represents the 1's value, another bit that represents the 2's value, another bit that represents the 4's value. Okay, and you can see that we have 1, 2, 3, 4, 5, 6, 7, 8 possible states of the 3-bit binary counter. What is a shift register? A shift register is a logic circuit. It's clocked, and it's an array of circuits that passes data in steps along the array. So if I put data here, and then I trigger the clock, it moves it over to here. If I trigger the clock again, it moves it over to here. If I trigger the clock again, it moves it over to here. At any point there, I can look and see what the data is at there. And the clock, of course, drives all of them. So it moves data through, passes data through the array, shifts it through the array as the clock operates the different steps. What are the basic components of virtually all sine wave oscillators? If you have ever worked with an audio system, a public address system, you know that the way to make a howling sound, which is an oscillation, is to have feedback from the speaker to the microphone. Okay? So what do you have? In your public address system, you have an amplifier, and you have feedback, and that's what makes an oscillator. Okay? A filter is also good because that helps you to control the frequency. Okay? In this case, we have an amplifier. We have feedback through this circuit that's designed to make it into an oscillator, and the crystal here is a filter that will allow only a single frequency, only one particular frequency, to be passed through the feedback circuit. So this closely controls what the frequency of the oscillation will be. But all sine wave oscillators are a filter and an amplifier operating in a feedback loop. How is the efficiency of an RF power amplifier determined? To find the efficiency, you divide the RF output power by the DC input power. Okay? So if we have a power amplifier here, we have a signal coming in. If we're putting 100 watts of DC power into the power amplifier, and we're getting out 60 watts. Now, in this case, they're showing a speaker, but it works the same way for radio frequency to an antenna. The principle is exactly the same. Then if we have 100 watts coming in, 60 watts coming out, then our amplifier, our efficiency is the 60 watts out divided by the 100 watts in, or efficiency of 60%. What determines the frequency of an LC oscillator? LC, the L means inductance, the C means capacitance. Correct answer is the inductance and capacitance in the tank circuit. Now here we have that same or a similar oscillator circuit for what we had before with the crystal. In this case, we have a bipolar transistor instead of the FET that was in that one. But here, instead of the crystal, we have a tuned tank circuit here that does the filtering or controlling the frequency of the that will be passed through. The oscillator will be allowed to oscillate out. Okay. So here, the frequency of the oscillator is determined by the inductance and capacitance in the tank circuit. Which of the following is a characteristic of a Class A amplifier? A Class A amplifier is operated in a region that has very low distortion. Which of the following modes is a Class C power stage appropriate for amplifying a modulated signal? Okay, now this is a little tricky because you may not consider CW to be modulation, but it is, and it's the correct answer here. Turning the signal off and on is impressing information on it, which is the definition of modulation. And the CW is the only one here that the Class C amplifier is appropriate for, because if you put voice through if you put an amplitude modulated voice, either single sideband or double sideband with a carrier modulation through a Class C amplifier, the signal will be distorted. And depending on how much distortion, it may not even be understandable. But the CW, where you're not changing the envelope, just turning the envelope on and off, can go through a Class C amplifier without distortion. Which of these classes of amplifiers has the highest efficiency? The Class C has the highest efficiency, but it has the disadvantage of distortion, which is not tolerable for some kinds of signals. What's the reason for neutralizing the final amplifier stage of a transmitter? Remember, amplifiers like to turn into oscillators, and if the final amplifier stage of a transmitter has any kind of feedback, either intentional, well, it wouldn't be intentional because it wouldn't be an amplifier if it was intentional. But anything that is unintentionally causing feedback in the amplifier stage, it would cause it to oscillate or become a self-oscillator. So then you neutralize it to tune out or to block out any feedback that could occur in that amplifier stage, and that way it amplifies but doesn't oscillate. Which of the following describes a linear amplifier? This particular question is a trap for CBers because they're going to grab this answer that says any RF power amplifier used in conjunction with an amateur transceiver. The actual answer is an amplifier in which the output preserves the input waveform, and that's what is meant by linear. You put a signal in to the amplifier, it comes out with the same waveform, just more power. So linear preserves the input waveform. Linear preserves the input waveform.